Okay, so now let us then come back to the problem of understanding rotation in general. So without this fixed axis assumption and all that, right? And for that, so before we go into details of it, let's start with this problem that we already discussed earlier of sorry, so this is not of a conical pendulum. Right, and there what we did is we basically demonstrated that we can realize this problem in two different ways. One, if setting the origin here, right, about the center of this circle which the conical pendulum makes, right, and then we found out if this is the case, then there is only one component of angular momentum Lz, which then nicely coincides with our angular velocity omega or angular speed. And we could also do this about this pivot point A, right, and when we did that, we can go back and look at the results. What we got was that the total angular momentum about this point doesn't have a fixed direction, in the sense that it's not pointing in the z direction. Rather, it has two components: the radial, we wrote it as L rho, and the vertical Lz. Right. So what that means is, at any given instant, my total L is pointing in some direction like this, making some angle with one of the coordinate axes, right? So then this is my total angular momentum, right? And this was the direction of omega, right, in this case. So now what we see is, so this is the problem that we nicely kept aside. We did not dwell anything much on this, but then this is the problem of a general rotation, that there could be a case where the total angular momentum vector is not pointing in the direction of angular velocity vector, right? So, and that is why that fixed axis rotation was a special case, because when we said fixed axis rotation, we always implied that the angular momentum or the component angular momentum which is under consideration is pointing in the direction of angular speed or angular velocity, right? In general, that is not true, and if this is not true, then what happens is, in case of fixed axis rotation, so for fixed axis rotation, right, we wrote down Lz as equal to I omega, right, where omega is also in z direction. We can write down, well, omega has only one component at this moment. This I was called moment of inertia, and we then derive the expression for this. And this is taken as a scalar quantity, right? If that's the case, now knowing that omega is a vector quantity with components, I can write down, again in case of fixed axis rotation, I can still write down L vector as this scalar and omega vector, right? And when writing down like this, when we write it down like this, what we are saying is, implicitly, we are saying that L points in the direction of, or L vector is in the same direction as omega vector, right? However, that's only true for fixed axis rotation. In general, L can be in any independent direction with respect to omega cap. So then, for general rotation, right, this expression is not true. We cannot write it down like this. It doesn't make sense, because if L vector is equal to some scalar into the omega vector, then both the directions have to be same. And if the directions are different, then we just cannot simply multiply a scalar to a vector and get that, right? So now we have to find a different relationship, right, or a proper relationship between the vector L and vector omega. So let's do that, and to do that, what we'll do is we'll start with the definition of angular momentum. So now I will do this. So let's write down L and omega for general rotation. Right? So we are looking for a relationship between this. So let us first write down, well, definition of L. So angular momentum about center of mass, because we know that for any given rigid body we can write down angular momentum, total angular momentum as the angular momentum of the center of mass and the angular momentum of the body about the center of mass, and problems with angular momentum of center of mass are straightforward, can be solved. So we are mainly interested in finding out the angular momentum about center of mass, and we wrote this down. So let us write down this L. So now this is I'll write down Cm here and then I'll drop this just to remove the clutter. So angular momentum about center of mass is then given as sum over I mi, well no, let's start with the one. Well, Ri cross mi Ri dot, right? This is the expression which we start. This is the basic expression. This doesn't change, right? So this is true for all cases of rotation, be general, be fixed axis, whatever, right? So now we can write this down as sum over I Ri cross, it's a cross product of two vectors, Vi, right? And now recall that we wrote down Vi as Ri cross. So again, now we are only considering where this vector Ri, right, is not changing its magnitude. So again, for a rigid body, considering rotation of any part of it about the center of mass, we know that the position vector is simply going to rotate. It cannot change because the particle is not going to shift, right? So the expression we got for V as omega cross R holds true here. So we can write this down as mi omega omega cross R, right? We can write it down like this. So then this is my expression, and now all we have to do is solve this. So I can write down then my total L is sum over I mi Ri cross omega cross Ri. Okay? And now solving this is simple. It's just A cross B cross C. So you can try to find out what will be the resultant of this. What I'll do is, I'll not do the algebra, it's straightforward, you can do it. I'll simply write down the components of L now in terms of x, y and z. When we take this cross product, we will get a big expression with components pointing in i cap direction, j cap direction, k cap direction if we decompose this into x, y, z. So by doing this, what I am saying is, let us take Ri. So you can, to do this, you can decompose Ri as xi cap plus yj cap plus zk cap, and similarly omega as omega xi cap plus omega yj cap plus omega z k cap, and we can do this because we have established that omega is a vector, so we can simply write it down in its component form, find this cross product, right? And what we'll get is, we'll get Lx, the x component of this is basically x component of this expression, and that would be sum over I mi y square plus z square omega x minus sum over I mi x y omega y minus sum over I mi x z omega z. So this you can try to show that if you take this cross product, this is what we are going to get. Similarly, now just by looking at this one, I can also write down expression for Ly and Lz. So for Ly, this will be sum over I minus mi xy omega x plus sum over I mi x square plus z square omega y minus sum over I mi, this should be yz omega z, and similarly for Lz this will be minus sum over I mi xz omega x minus sum over I mi yz omega y plus sum over I mi x square plus y square omega z. Right? So basically we get these three components for each Lx, Ly, Lz, and what we find out is that in a general case, now the components of each component of angular momentum, right, is not dependent only on the angular velocity along that direction. So Lx is not only dependent on omega x, angular velocity in the x component of angular velocity, but also the omega y and omega z, right? So now it's a complicated expression. What we can do is, very quickly, we can write it down in a more compact form, right? So, and we can again recall from our discussion of the rotation of axes in I think the previous lecture, where we could write down the rotational transformation in the matrix form. So exact same thing we can do here. And now I can write down Lx, Ly, Lz as a column matrix, and then this becomes my transformation matrix, or which is going to establish relation between omega x, omega y, and omega z, right? Okay. And what are the components here? These are the components. So this is sum over I mi y square plus z square minus sum over I mi xy minus sum over I mi xz, yes, xz. Similarly, minus sum over I mi xy plus sum over I mi x square plus z square, and then minus sum over I think of y z. Here minus sum over I mi xz minus sum over I mi yz plus sum over I mi x square plus y square. Right? So then this is the compact form, or in matrix form, we can write down the same relationship. We establish a relationship between the vector L and vector omega, and now we see that yes, since both are vectors and need not be pointing in the same direction, so the transformation is rather complicated. It's not a straightforward multiplication with a scale, right? And now L cap could be different from omega cap, right? Because it's a combination of individual components. Okay, this is termed as inertia tensor, so it's given another unique name, inertia tensor. So now we don't call it as a moment of inertia, right? But in a similar spirit, we call it an inertia tensor. Okay? Tensors are, well, again, these are mathematical quantities just like vectors or matrices, and they have special transformation properties which one would study in maths courses. Right now, we don't need to go too much into the details of tensor. All you need to know is this matrix will be termed as inertia tensor. It has 9 components. As you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9. It has 9 components, and a careful examination. So when you find out these components, you can readily see that not all 9 components are independent. Only 6 of these are independent. So 1, 2, 3, these are independent components. Y square plus z square, x square plus z square, x square plus y square. And rest of the 6 are basically doublets in the sense that you have xy, you have xy, you have xz, xz, and we have yz and yz, right? So with 6 independent components. Right? So this is the inertia tensor now. And now if I want to write it down like this, then basically I do is, I'll also identify that, let's say the first term, sum over I m I, y square plus z square, right? This is nothing but a term which could be written as, sum over I m I rho I square, right? Where what is rho I? Rho I is the perpendicular distance of the particle from x-axis, which is nothing but y square plus z square square root, right? So this is same as your sum over I m r square, and we can also write it down as for a rigid body in integral form as dm rho square, right? So it's the same thing. So this is the term which is your familiar moment of inertia, right? This is my moment of inertia, but about a particular axis, right? So this is the familiar moment of inertia about x-axis, y-axis, z-axis, right? So if I write it down in this way, then what I can do is I can write down this matrix Lx, Ly, Lz as, I'll write down this as I xx, and this is the moment of inertia. So this is simply your moment of inertia. This one I'll leave as it is and simply write it down in symbolic form as I xy. This I'll write it down as I xz. This again will be I xy. This will be I yy. This is also moment of inertia, right? And another term I yz. Similarly, I xz same as this, I yz same as this, and I zz, which is also then the familiar moment of inertia term, but about x-axis, y-axis, and z-axis, and the omega column matrix multiplied on this side, right? So this is another form way of writing this product of the moment of inertia here. The inertia tensor here, right? Okay. And as I said, these diagonal terms, so this one, this one, this one, these are called moment of inertia because they have the familiar form of sum over I mr square. These are called the moment of inertia about the axis, x-axis, y-axis, z-axis. These terms, remaining 6 terms, these are then termed as products of inertia, right? And they have this form, sum over I mi, I'll write it xi yi, but anyway, this could be anything, right? So, and of course, negative, right? So these are the product of inertia terms, and together with moment of inertia and product of inertia, one finds the inertia tensor, which now, using which, now we can write down our sought after relation. So now I can write down L vector as inertia tensor I, and to differentiate it, I'll put a tilde over it. So just to differentiate that this is not a scalar nor a vector, this is a tensor quantity, right? So it's a line component. It doesn't have a single component which carries only magnitude. It also does not have only 3 components which are sufficient to describe it completely, right? It requires in total 9 components, out of which 6 are independent to describe it completely. So L is inertia tensor and then omega vector, and yes, I has the property that I multiplied as a matrix multiplication, I multiplied by omega, right, will give us another vector L, where now we do not require L cap to be equal to omega cap. Now L cap can be in any direction, omega cap can be any direction, because I, which is the inertia tensor, is my transformation, which gives me relation between the angular momentum, the total angular momentum, and the angular velocity of any particle or any rigid body about any given axis. Right? So now we are not bound with a fixed axis rotation or rotation along the particular direction. Okay. So this is so far so good. Everything seems fine, and we have this defined relationship now. Another one which we always have, this one, with these two, we can define rotation, right, complete. All we require is the torque is the rate of change of angular momentum, and angular momentum is related to the angular velocity. In this way, with these relations now, we can consider general rotation of any rigid body, and we can try to start solving the problem. We can try to analyze the system. However, in doing this seemingly simple analysis, what turns out to be is that we could find the relationship between L and omega. However, the relationship that we found, the transformation matrix that we found, is rather complex, right? Because now, instead of just calculating this moment of inertia, which we could do nicely by writing integral dm r square, now we need to find out at least these 6 components, and then every time we have a change of axis, state of coordinate system, we need to evaluate these 6 components, right? So the problem, although we have a nice framework, the problem need not be that straightforward. It does seem more complicated right now. However, again, just because the world is not that complicated, what turns out is that we necessarily need not calculate the products of inertia all the time, right? So, what saves us, or what lets us actually calculate physical system is that, back chalk. Yeah, exactly this one. So for any rigid body, right, we can find 3 perpendicular axes, right? So we can find a set of 3 perpendicular axes for any rigid body, and that's needed because our coordinate system is defined as 3 perpendicular orthogonal axes, right? So for any rigid body, we can find 3 perpendicular axes in the body, right? For which this product of inertia term is equal to 0, right? In other way, what I am writing down is that if, let's say, 1, 2 and 3 are such axes, right? And what I mean by this is that, let us say this is my rigid body in 3 dimensions, then, and if I know that this is the center of mass, then roughly I can define a set of axes, let's call it 1, 2 and 3. I can find out these set of axes which are perpendicular to each other, right? And basically in one of the coordinate directions, right? Such that this matrix or the inertia tensor can simply be written as Ixx, not xx, 1, 1, 2, 2 and 3. And if we do this, then once we can write it down in this thing. So now by choosing, so basically by aligning our coordinate frame about these 3 principal axes for any body, by choosing x, y, z along 1, 2 and 3, right? Now what we do is, since only these 3 components remain, we can write down Lx, Ly, Lz as our standard expression or our familiar expression Ixx omega x, Iyy omega y and Izz omega z. Right? So we can get back to this simplicity, right? But the effort that one has to put in is to identify the set of principal axes, and then looking at the problem, choosing the coordinate frame about these 3 principal axes. But then again, the calculation or the analysis would look more familiar as we did in case of fixed axis rotation. And of course, the total angular momentum now still is Lx I cap plus Ly j cap plus Lz k cap. Right? Okay. So let me end by giving a hint of these principal axes. Right? You might have some idea by now, or you may have gotten some idea that what could this principal axis be. So for example, okay, so these will be called then, so let me just write it down here. Principal axis 1, 2, 3. Okay. So for example, let's say one uniform sphere. Right? So if you have a uniform sphere like this, right, this center of mass could be hollow, could be solid, doesn't matter. Right? Then any set of 3 axes, for example 1, 2 and 3. So any set of 3 axes which are along one of its diagonals, one of its diameters, right? So you can always define 3 diameters for a sphere, and passing through its center of mass will work as a principal axis, right? So all axes along diameter, and if they are along diameter, then they are going to pass through origin and passing through center of mass. Right? Are its principal axis? So because that's a completely symmetrical problem, so there is no problem in finding out Ixx, Ixy, Izz. In fact, for a sphere, all these 3 are going to be exactly the same, right? And we can see this when we discuss different problems. Another example that we can take is, let's say, cylinder. So we are not considering completely non-uniform, irregularly shaped rigid bodies, because there the problem is rather more complicated. But for most of the cases where the rigid body is symmetrical, or we can find out some symmetry in the system, the task is not technical. So let's say for a cylinder, right, so which looks something like this, we can define these 3 axes again. So the one along the axis of the cylinder, right, is a principal axis, so we'll call it 1. This is a principal axis, and then any 2 axes which are passing through its center of mass and perpendicular to each other in the horizontal plane, in the perpendicular plane, or in the normal plane to this principal axis are also principal axis. So then this could be 2 and this could be 3. Right? So this way we can try to find out different set of principal axes. For example, again another example I can show you is say a rectangular sheet of paper, right? Then you can look at the symmetry. So we can have one principal axis here, another principal axis here, and the third one is going into the board, which is normal to the plane of this paper. Okay. So anyway, in the next one, then we'll try to see how to move forward from here.